we continue with multilayer perceptrons. As I had mentioned in the last lecture, we use a approximation of the step function, which is the sigmoid function. So, instead of having something like this, we have something like this. Okay. And this sigmoid function has this one many possible algebraic equation forms are have the same, for example, tan hyperbolic and other functions have a similar S shape. This is a S shaped function. One of the popular function used is this form. So, the name sigmoid is for a general class of S shaped function. This is one particular form. The other form, for example, f x equal to tan hyperbolic x is also of this form. Okay. The good thing about this particular form is that you can compute the derivative of this function from the function itself. So, if you take the derivative with respect to x, you will find that it is nothing but f x into 1 minus f x. So, the value of the function into 1 minus the value of the function. Okay. So, that becomes the derivative. So, if you plot the derivative, it is f x into 1 minus f x. Okay. Sometimes actually another form that is popular in deep neural network is that because you have something called a rectified linear unit. I will quickly explain it. Saturates to plus 1 and minus 1, in between it is like this. So, this is sigmoid. Sometimes you have unit which is like this, does not saturate, just keeps on increasing, all right, or maybe in a special case it is just like a proportional type. So, y is some constant time x. All right. So, this is about the activation functions. So, the multilayer perceptron has two extensions over the normal perceptron. It has hidden layers, and instead of a step activation, it uses a sigmoid activation. So, that derivative can be easily taken. Now, let us come to the problem of finding out the proper set of weights. So, we will use the same methodology. We will use the same methodology. So, let me draw the picture. I am drawing only one hidden layer. Just roughly drawing it, and there are weights. So, this is 1 1 1 1. Okay. So, as I mentioned, the weight, the superscript is the layer numbers from which layer to which layer, say layer m to layer n, and the subscript is that which neuron to which neuron, ith neuron of mth layer to jth neuron of nth layer. That is how I terminate the weight. So, the steps are that following. initialize all the weights to random values, just like the normal perceptron. Then update weights, I will explain in detail, and finally stop when delta W, change in weight value, update value is small over successive iterations. Okay. So, but so this is same as the multilayer perceptron, but the only thing is that this weight update is now more complex than the perceptron. Now, it has two steps: forward propagation and backward propagation. All right. So, I will explain this in detail, but the philosophy is something like this. It is like suppose you are trying to say park your bike. So, what you do is you first see the current orientation of the bike and just place it. If it does not fit well, you use the amount of error as a feedback, amount of mistake you made as a feedback, and change your position again. Okay. So, that means once with the current estimate of the values, you try to do the task, and amount of error you make in the task, use that as a feedback to correct your current position, to change your current position, correct your current position, right. So, you first, so it is like you are trying to solve some problem, you first solve it using whatever knowledge you have, then you see how much error you have made, use that error to correct your knowledge again. Okay. So, and do this repeatedly till you get the answer to certain accuracy. So, I will explain these two steps. First, I will explain forward propagation. So, this is my network. This is my network, and at any stage of the training, say maybe the initial stage or some intermediate iteration, all these links will have some weight value, some value, maybe not the correct value, but some value. Some value of the weights in that iteration, whatever iteration. In that iteration, whatever may the value of the weight. Then what you do, note that. So, look at every training example. Let us say x1, x2, x3. Okay. So, what you do, you have these values and then use the weight value and do two steps, add up, add activation, apply activation function. So, let me properly write it down. Compute xi, okay, over all the xi's, all the inputs, and then apply activation function. So, layer by layer, first for this all these neurons, then their output as input to this for all these neurons, finally output you get. So, that means for every input for this set of weights, this is the output. That means, we are propagating the input to the output, that is why it is called a forward propagation. Now, this value of output you get, it may not match the desired output. So, let me call it as Ti. Okay. Let me call it the desired output as target output Ti. So, this why this forward propagation produces may not match. Now, you compute the error. Put mean squared error. Now, you compute very simple, you know yi you have computed actual output by forward propagation, subtract from Ti, take the square, add up over all the training examples. Okay, that is your and take the average over all this. So, that is the mean squared error. So, forward propagation will find out this mean squared error. Now, next step. So, forward propagation it propagated not this propagated the x values to the output, computed the y, take the difference with Ti, compute error. Now, this error you feedback, as I had mentioned earlier, you feedback and update the W's. So, yes, update. What is the update? Same form. W new is W old plus some learning rate eta times delta W. Okay. And this delta W gradient descent, simple way of it. Take all the weights, not, there will be more weights. Take the surface, whatever your value of W old is, you move it to W new, in the direction of the steepest descent. So, delta W is derivative of this error function E, the tangent, the steepest descent. I will go through the derivation of this. I will go through the derivation of the delta E, delta W. So, this is my okay. Sorry, I forgot this half term in the error. You can as well add a half term. So, this is the error. Yes, sir. I am just doing it. This is the thing, this is the thing, and this is the thing. You just follow these steps, right? You just if you just go through the steps, I am just taking normal derivative. Okay. So, if you have followed it, is there in the uploaded slides. If you have followed it, then these terms can be further expanded like this. Okay. Where net is this summation or W I x I. Xi from the previous layer. Okay. And this O is f of net, f is the sigmoid. If you write down from the previous property that f x you get this, which is this. Similarly, if you do this, you get this. All right. So, if I go on further, this is my update rule. For the weights between output and hidden. Similarly, you can repeat this where output will become the output of the hidden units for the output to input. So, this way you keep on doing, and you call this as a gradient descent backpropagation algorithm. So, this is the so called this is the rule. Okay. So, now again there can be a incremental or a gradient, that means either you take error to be sum of all the thing or for a single update. So, this is batch, you can have a single. So, not batch, sorry, this is incremental. For every training input you update. Earlier as waiting, as accumulating over the entire batch of training input, then updating. So, that is why this sigma is there. But the functional form is same. So, this I summarize here. Propagation. Okay. So, this is the thing. Right. If you look at the steps, just whatever I discussed, this is the step. This is the steps, whatever I discussed, just I am written it down as a single step by step thing. Okay. So, this is delta. This actually is sometimes called the delta value. Okay. And with delta w, so this is this delta k, delta is actually the derivative we are talking of, and delta w is learning rate times the delta times xij. If you remember perceptron, this delta was not there, eta times xij only was there. Okay. So, here is an example. If we just take these inputs and propagate, you will have this kind of delta values. I want you to go through these examples. This is the rule I explained, you should by hand work it out. Okay, so, this is a very powerful rule. It is can be generalized to any number of hidden layers, and although some of the one of the disadvantages, if you increase the number of layer, it becomes slow. There is another disadvantage, is the convergence. In the perceptron, the error surface looked like this, a parabola. So, this gradient descent will always work. This is perceptron. Whereas, for the multilayer perceptron, this error surface may look like this. These are the local minimas. And this is the now, depending on your initialization random values of the w, your gradient descent may get you stuck in a local minima rather than a global minima. So, training always may not give you the least error. So, that may happen, right. So, this is a limitation of the backpropagation algorithm. There are ways to rectify it by adding something called a momentum term, which will sort of throw you out of this local minima, so that you come here. So, those expressions are there. Here is the momentum term. You can add additional term proportional to the velocity of that point, so that it rolls down till it reaches the lowest point. So, how to use this multilayer perceptron? Here is an example. Suppose I want to recognize people, person's face, biometric. So, you know images are represented as pixels of matrix of pixel values, some gray values 0 to 55. Each of these values you input to a neural network, and then have hidden layer, and the output maybe is the ID of the person. Sorry, again this type of connection will not be there, it is only from one layer to the next layer. Okay. And you know that this person's ID is say 231, another image comes, another training example, some other ID. This is the desired output, this is the output. You repeatedly iterate through forward propagation, back propagation till your weight do not change, and that would give you when a new image comes, it will predict which person ID it is. Right. So, this has been very popular in many applications, this is popular, and I would request you to try out neural network on some problem. There are some issues like you cannot interpret, this is connectionist, you do not know any logical rule which gives this. There is a problem of overfitting, it is like you can there is a problem of overfitting, that means after some time if you increase the number of hidden layers, it fits the training data very well, but sacrifices the generalization error. Okay. So, so the basic problem is how deep a network, how many hidden layers you should take to solve a problem, or there is no real solution, you have to do trial and error. There are methods like regularization to control how many neurons you should have. So, those are some problems you would face with, but it is very popular, especially with complex tasks like stock market prediction or climate prediction, it is very popular. Okay. So, these are the reason is that it is a very it has very lot of expressive power, many complex functions it can realize. There are many extensions like I said before, backcast, feedback, recurrent network, there is a self-organizing map. There are many other numerous type of neural network, but this is the most popular that we will use in data mining, and many commercial software actually implement it. So, I request you to just write a small program to train this backward propagation for a small network on some task and do it. I hope that will help you. So, this closes my discussion on the neural network, only the multilayer perceptron and the perceptron. I am not time to go to other, you can read it from the notes and other sources I will give you, but it is a very popular tool.